Hoover Dam was not just poured into a canyon, it was a concrete mountain so huge that if engineers had built it like one solid block, parts of its core could have stayed dangerously hot for more than a century. The problem was chemistry. When concrete cures, it releases heat. In a sidewalk, that heat escapes. In a dam holding back the Colorado River, the heat gets trapped deep inside. The outside hardens first, the inside keeps expanding, and then the structure can crack from its own temperature difference. So the threat was not only the river, the cliffs, or the height, it was the dam cooking itself from within. To stop that, engineers buried a cooling system through the concrete. Hundreds of miles of pipe, often sited at about 582 miles, carrying chilled water through the fresh pores. They had to solve a strange problem in construction history. How do you build a mountain of concrete without letting it tear itself apart? Black Canyon was not an easy place to build anything. The Colorado River cut through steep rock walls on the border of Nevada and Arizona, carrying snowmelt from the Rocky Mountains toward farms, towns, and cities that increasingly depended on it. But the river was unreliable. Some years it flooded with destructive force. Other years, it did not deliver enough water where people needed it. A dam in this canyon promised control, hold back floods, store water through dry seasons, and turn the river's drop into electricity for a growing Southwest. That promise required a structure on a scale the United States had never attempted. Hoover Dam would rise more than 700 feet from its foundation and curve across the canyon like a thick concrete wall wedged into stone. It was not just tall, it had to be massive enough to resist the pressure of an entire reservoir pushing against it. The amount of concrete was almost difficult to picture. The dam itself used roughly 3.25 to 3.3 million cubic yards of concrete. That does not include every associated structure around it. Just the dam contained enough material to build a highway across a large part of the country, depending on the width and thickness you imagine. For most people, concrete means a driveway, a sidewalk, a basement floor, or the foundation of a house. Workers pour it, level it, let it cure, and the heat produced inside can usually escape into the air or the ground. Hoover Dam was different. In places, the concrete was hundreds of feet thick. A normal pour spreads heat over a thin slab. This project trapped it inside a mass so large that the center could not cool naturally on any useful schedule. And the schedule mattered. The dam was being built during the Great Depression, with thousands of workers, enormous political pressure, and a river that had to be diverted, controlled, and finally restrained before it could reclaim the canyon. So engineers faced a problem that sounded backward. Concrete gets stronger as it hardens. That is why we build with it. But if concrete hardens all the time, why would pouring more of it become dangerous? Concrete does not harden because the water simply disappears. It hardens because water reacts with cement in a process called hydration. Cement is made from minerals that have been heated, crushed, and ground into a fine powder. When water is added, those minerals begin forming new microscopic crystals. These crystals grow around the sand and gravel in the mix, locking everything together into a solid artificial stone. That chemical reaction gives off heat. In a sidewalk or a house slab, that heat is not usually a crisis. The concrete is thin enough that warmth can move out into the surrounding air, the ground below, and the exposed surface above. The slab may get warm, but it does not become a giant insulated furnace. Hoover Dam changed the scale of the problem. A thick block of concrete has a small amount of exposed surface compared with the huge volume inside it. Heat produced near the outside can escape. Heat produced deep in the middle has a much longer path to travel. If engineers had poured the dam as one continuous mass, the interior would have stayed hot for years. Some estimates said natural cooling could have taken more than a century. That was not just inconvenient. It meant the dam would be changing temperature long after it was supposed to be finished, filled, and holding back water. The danger came from uneven cooling. Hot concrete expands, cooler concrete contracts. In a small pour, the temperature differences are usually modest enough for the material to tolerate. In a structure hundreds of feet thick, the outside could cool and shrink while the interior remained hot and swollen. That sets up internal stress. The outer concrete is trying to pull tight around a core that has not finished contracting. The inner concrete is still expanded, pushing against cooler material that wants to move a different amount. Concrete is strong under compression, which means it can take enormous squeezing forces, but it is much weaker in tension when it is being pulled apart. Cracks were the nightmare scenario, not small surface blemishes, but fractures that could reach deep into the body of the dam. Every crack would be a path for water pressure, a weakness inside the very barrier meant to restrain Lake Mead. So the challenge was not only pouring enough concrete, it was controlling the invisible heat being born inside it. The simplest construction plan was also the impossible one. Build a form, keep the concrete trucks coming, and pour Hoover Dam as a single gigantic block. On paper, that sounds efficient. No seams, no interruptions, just one continuous artificial cliff rising across Black Canyon. But inside that cliff, the hydration reaction would have turned the dam into a slow-cooking mass of stone. The numbers make the problem almost absurd. Hoover Dam required millions of cubic yards of concrete. If all of that material had been placed as one monolith, the heat trapped in the center would have had only one way out, inch by inch, through hundreds of feet of surrounding concrete. Widely repeated estimates said that without artificial cooling, the dam might have needed roughly 125 years to cool naturally. That did not mean workers would simply wait a century and then cut a ribbon. It meant the dam would still be physically changing across generations. Imagine finishing the structure, filling the reservoir, and then knowing that deep inside, the core was still warmer than the outside and still shrinking toward its final size. The concrete would not behave like one calm, finished object. It would behave like different zones locked together while trying to move at different rates. The faster the crews poured, the worse that conflict became. Every fresh load added more reacting cement, and every new layer buried the heat from the layer below. Speed, which was essential for completing the project, also increased the thermal trap. This was the engineering contradiction at the heart of Hoover Dam. The builders needed momentum because the project was enormous, expensive, and politically urgent, but concrete at that scale punished momentum. A single uninterrupted pour would have created a body too large to cool safely and too stressed to trust. So the solution began with an admission that sounds backwards. To build one dam, they first had to stop thinking of it as one dam. They had to divide it into smaller pieces that could be poured, cooled, measured, and controlled. Only after those pieces had survived their own heat could they be locked together into the final structure. Hoover Dam had to be broken apart before it could become whole. Instead of one endless pour, Hoover Dam was built as a grid of separate concrete columns, almost like a stone jigsaw puzzle assembled inside the canyon. Engineers divided the structure into roughly 230 interlocking blocks. Each block had its own boundaries, its own schedule, and its own cooling problem to solve. From the outside, the finished dam would look smooth and continuous. During construction, it looked more like a rising city of concrete cells. Inside each cell, crews did not dump concrete from the bottom to the top in one shot. They placed it in horizontal lifts, commonly about 5 feet high. A lift would be poured, spread, vibrated to remove air pockets, and allowed to begin hardening before the next lift went on top. That method gave the builders control. If a section was running too hot, they could slow down. If a block needed inspection, they could reach it before it was buried under hundreds of feet of new material. If one part of the dam was ahead of another, the schedule could be adjusted without stopping the entire project. The block system also helped with shrinkage. As concrete cooled, it contracted. The whole dam had been one continuous mass. That movement would have pulled against itself across enormous distances. By splitting the dam into columns, engineers gave each section a more manageable volume and a defined place to move. But these blocks were not meant to remain separate forever. Their sides were shaped and arranged so the columns could lock together into the final curved gravity arch. The dam still had to act as one structure when the reservoir pushed against it. So the plan was not just to chop the dam into pieces, it was to build those pieces in a controlled order, manage their temperature, and then connect them into a single wall strong enough to hold back the Colorado River. For construction logistics, it was a brilliant compromise. Materials could be delivered to specific cells. Crews could work in multiple areas at once. The dam could rise in stages instead of waiting for one impossible monolith to cure. But the compromise only reduced the scale of the heat problem. It did not erase it. Even one of these smaller blocks could contain thousands of cubic yards of concrete. That was still enough mass to trap heat deep inside, shrink unevenly, and crack if left alone. The dam had been divided into controllable pieces. Now those pieces needed something far more aggressive than patience to cool them. A single lift began far from the canyon wall at the batching plant. There, the recipe had to be controlled before the concrete ever reached the dam. Aggregate was sorted by size, from sand up to coarse rock. Cement was measured in exact amounts. Water was added carefully because too much would weaken the mix and too little would make it impossible to place properly. This was not a few men turning a drum on a job site. It was industrial scale production, feeding a schedule that had to match the rising grid of blocks. Each batch was made for a specific placement area and the timing mattered. Once cement and water met, the clock was running. The fresh concrete moved out in huge buckets carried by cableways stretched across the canyon. From above, the system looked almost impossible. Steel cables, suspended loads, and crews guiding heavy buckets toward individual block sections hundreds of feet below. For a moment, this is what the job sounded like. When the bucket reached the right block, workers released the load into a prepared section. The surface below had already been cleaned and readied, so the new lift could bond to the one beneath it. Forms held the edges. Embedded pipes, inspection points, and block boundaries had to be protected as the concrete spread. Then came the handwork. Crews pushed and guided the wet mass into corners, around obstacles, and across the lift. They used tools and vibrators to consolidate it, shaking trapped air out of the mix so voids would not remain inside the dam. After that, the top was levelled to the correct height, ready to become the base for another lift later on. From the outside, this looked like a controlled routine: mix, carry, dump, vibrate, level, repeat. But inside the fresh placement, a chemical reaction had already started. As the cement hydrated, it released heat. In a sidewalk, that heat escapes quickly. In a Hoover Dam block, surrounded by more concrete and canyon heat, it had nowhere easy to go. The same lift that workers had just smoothed into place was quietly turning into a thermal problem. By the time the surface looked calm, the interior was beginning to warm, and every new lift added more mass above it, making the heat harder to escape. The answer was not just to pour smaller blocks. Engineers also turned the dam itself into a cooling machine. Before a block was filled, crews placed steel pipes through the empty formwork, arranging them in coils and runs that would be buried inside the concrete. As each lift went in, the pipe network disappeared from view. By the time the surface was levelled, those lines were sealed inside the mass, waiting to carry heat out from the centre. Across the whole project, the cooling system is often described as about 582 miles of pipe, or nearly 600 miles. That headline number is hard to picture, but it meant the dam was not just a stack of concrete blocks, it was a stack of concrete blocks threaded with a hidden circulatory system. Once the concrete began curing, water was pushed through the pipes. The water entered cooler than the surrounding concrete, absorbed heat as it moved through the buried lines, and then carried that heat away when it came back out. Instead of waiting for the centre of each block to cool naturally over years, engineers forced the heat to move. The pipes had to be installed with the pour schedule in mind. They could not be added later, because once the concrete hardened, the interior was sealed. Workers had to position the lines before and during placement, protect them while wet concrete flowed around them, and make sure they stayed open for circulation. This was a precise solution to a specific danger. If the outside of a block cooled and shrank while the inside stayed hot and expanded, stress could build inside the concrete. Too much stress could create cracks, and cracks in a structure holding back the Colorado River were not a minor defect. So the buried pipes gave engineers control over a process that otherwise would have been too slow and uneven. They could cool the interior of a block while construction continued above it, reducing the temperature difference between the core and the outer surfaces. At first, the cooling water came from the Colorado River, That made sense. It was already on site and it was cooler than the curing concrete. But as the dam rose faster, the heat problem grew with it. River water could remove heat, but not fast enough for the pace the builders were trying to maintain. The hidden pipes were only half the solution. The next step was to make the water much colder. The first cooling stage was simple in principle. Take water from the Colorado River, send it through the buried pipes, and let it pull heat out of the fresh concrete. For a while, that was enough to start bending the temperature problem back under control. But the river was not a magic coolant. Its temperature changed with season and conditions, and even when it was cooler than the concrete, it could only absorb so much heat on each pass. The dam was rising block by block, and each new pour added more hot curing concrete to the schedule. So the builders added something more aggressive, a refrigeration plant. This was not a small icebox sitting beside the canyon. It was an industrial cooling operation designed to chill the water before it entered the pipe network. The system used ammonia-based refrigeration, a common choice for large industrial plants because ammonia could move heat efficiently at the scale they needed. In effect, the project gained a second loop. River water could begin the job, but mechanically chilled water could finish it. Water was cooled down at the plant, circulated through the pipes inside the dam, warmed as it absorbed heat from the concrete, and then sent back to be cooled again. That changed the pace of the whole operation. Engineers were no longer limited to whatever temperature the river happened to provide. They could drive colder water through selected blocks and pull heat out faster during the critical curing period. The refrigeration plant was powerful enough that accounts often describe it as capable of producing huge blocks of ice, around 1,000 pounds per day. That detail sounds almost like a sideshow, but it helps show the scale of the machinery involved. This was the kind of equipment built to remove serious heat, not just cool a room. And the heat it was fighting was enormous. Every fresh lift of concrete generated more of it through hydration, the chemical reaction that turned the wet mix into solid stone. The pipes gave that heat a path out. The refrigeration plant made the path colder. By the time the system was working at full force, Hoover Dam was not simply being poured and left to cure. It was being actively temperature controlled from the inside, with river water, chilled water, and hundreds of miles of embedded pipe turning the concrete itself into part of the cooling system. From that point on, cooling the dam became a careful waiting game. The engineers were not trying to shock the concrete into getting cold as fast as possible. Each block had to be brought down in a controlled sequence, because concrete does not like sudden temperature differences. If the inside of a block stayed hot, while the outside cooled quickly, the two zones would expand and contract at different rates. That could create the same kind of internal stress the pipe system was meant to prevent. So the cooling water was managed block by block. Crews tracked temperatures, adjusted circulation, and waited for readings to fall into the acceptable range. The dam was not one giant slab cooling evenly from top to bottom. It was a grid of separate pours, each with its own progress, its own pipe loops, and its own timing. This mattered because the blocks still had to become one structure. When Hoover Dam was poured, small spaces were left between neighbouring concrete blocks. These contraction joints allowed the concrete to shrink as it cooled instead of tearing itself apart. But those joints could not stay open forever. Before the dam could be fully locked together, the concrete had to cool enough that most of its shrinkage had already happened. Only then could workers grout the joints and seal the mass into something closer to a single solid wall. That made the schedule brutally delicate, cooled too slowly, and major steps in construction had to wait. Push the cooling too hard or cool one area much faster than another, and the dam risked building stress back into itself. The solution was not just more cold water, it was measurement, patience, and control. By the time the readings finally came down, the cooling system had done something extraordinary. It had removed enough heat to let one of the largest concrete structures on Earth finish becoming stable. But that left a strange problem buried inside the dam. Once the concrete was cooled, what happened to all those pipes and gaps inside it? The answer was not to pull the pipes out. By the time the cooling system had finished its work, those thin metal lines were buried deep inside concrete that was never meant to be opened again. Removing them would have been impossible without damaging the very structure they had protected. So crews turned the temporary cooling network into a permanent part of the dam. They pumped grout into the pipes. This grout was a fluid cement mixture that could flow through narrow spaces, then harden in place. It filled the empty cooling lines so they would not remain as hollow tubes inside the concrete. Once sealed, the pipes were no longer a circulating system. They became buried remnants locked into the mass they had helped cool. But the pipe grouting was only part of the final step. The bigger structural job was at the contraction joints between the concrete blocks. Hoover Dam had been built as hundreds of separate sections because pouring it as one continuous mass would have trapped too much heat and produced destructive cracking. Those sections had been allowed to cool and shrink on their own terms. Now the gaps between them had to disappear. Workers injected grout into the spaces between neighbouring blocks and columns, filling the joints from inside. The material had to spread through the seams and bond the separate pores together. This was not cosmetic sealing. It was what changed the dam from a carefully stacked collection of cooled blocks into a unified structure. That transformation was the whole point of the cooling system. Each block had been treated almost like an individual patient, with its temperature watched and controlled. Once the readings were right, grout could lock that block to the ones around it. Across the dam, section by section, the internal grid was erased. What had started as hundreds of controlled pieces became one integrated concrete mass, strong enough to resist the enormous push of Lake Mead behind it. The cooling pipes were never the final structure people came to see. They were tools hidden inside the work, used for a short and critical phase. But without them, the concrete might have cracked before it could be joined. And without the final grouting, all that careful cooling would not have become a single dam. That is the payoff of the entire project. Hoover Dam was not just a problem of moving rock, setting forms and pouring concrete. It was a problem of controlling what happened after the concrete was placed. Every cubic yard brought strength, but it also brought heat. In a structure this large, that heat could not escape fast enough on its own. So the engineers had to design the dam around a simple chain reaction. More concrete meant more heat meant cracking, and cracking could have threatened the structure before the reservoir ever filled. The cooling pipes broke that chain. They turned the inside of the dam into an active construction zone even after the concrete had disappeared from view. Cold water moved through buried lines, temperatures were measured, blocks were cooled in sequence, joints were grouted only when the concrete was ready. The dam was not allowed to simply cure and hope for the best. It was managed from the inside. That is what makes Hoover Dam more than a monument to scale. The visible dam is the curved wall, the intake towers, the spillways, the road across the crest, and the huge face people photographed from the canyon. But inside that famous concrete mass is the record of a second project. Hundreds of miles of pipe, temporary refrigeration, temperature control, and final grouting that made the structure behave as one body. The result is easy to recognize and hard to fully see. Millions of people look at Hoover Dam and see one of the great construction achievements of the 20th century. They are right. But the dam also survives because engineers understood that concrete this massive could damage itself while it was becoming strong. They did not merely pour enough material to hold back the Colorado River. They built a system to stop that material from cooking itself inside Black Canyon. And nearly all of that system is now invisible. The pipes are sealed, the joints are buried, the cooling plant is gone. What remains is the dam itself, standing as proof that sometimes the most important engineering is the part no one can see. Hoover Dam's hidden lesson is that strength was not just poured into place. It was controlled, measured, cooled, and locked together before the river ever pressed against it. 582 miles of pipe turned a dangerous chemical reaction into a construction process engineers could manage block by block. Thanks for watching. In the comments, tell me which hidden engineering problem you want covered next. Tunnels, bridges, skyscrapers, canals, or something even stranger. If you want more infrastructure stories where the most important parts are buried out of sight, subscribe to the channel. The concrete is what everyone sees. The cooling system is why it works.